There we go. Okay, so we are looking at what are called standard electrode potentials. So we talked last time about voltaic cells or galvanic cells. So what we're going to learn how to do today is if you have two metals provided, or if you are given the setup for one, you can figure out how to label everything. So what's the anode, what's the cathode, what's the total voltage being generated, which one's increasing in size, decreasing in size, etc. So we'll go through how to do a couple of those. That's kind of the main idea of what we're doing here. If you saw in Google Classroom the schedule for the week, I'm going to have to redo that whole schedule that I gave you, but for this week, all we're going to do is today we'll finish that section of notes that we were supposed to do on Friday. Tomorrow will be kind of a work day, catch-up day for balancing redox reactions and doing these voltaic cells. Wednesday, we'll meet at 9:30 if you want, just to do some review for the homework quiz. So the only two things on the homework quiz are going to be balancing redox. So there'll be one acidic, one basic, and then one of these voltaic cells, like the examples that we'll go over today. So on Wednesday morning, we'll go over all of those. We'll kind of do almost like a little practice quiz together. Then I'll post the quiz, and then you'll just have to have it done by 8 o'clock that night, just like what we did last time. So you can work with a partner if you want, get it done right away, do it on your own, whatever you'd rather do. That way you'll have a nice long weekend, have a break, and then we'll come back at it on potentially Wednesday. They're talking about maybe making that Monday after Easter be the professional development day. Tuesday, you guys already had a scheduled day off, so I'm not going to take that away. So that means we would come back on Wednesday and finish the chapter, go through everything, and kind of get ready for the test. Okay, so that's kind of the overall plan for this week. Short week, just kind of a review. This is the only thing new that we're doing this week, and then next week we'll come back at it. Okay, so what we're looking at today is how to actually use that setup for a voltaic cell to figure out what kind of voltage you could generate. So when you look at what's called the standard electrode potential, these are the potentials of those half cells in an electrochemical cell. So remember, the half cell was what was going on in each of those beakers on either side. That's the potential of those different substances to generate electricity. They're all compared, so there's a table of these. They're all compared to what's called the standard hydrogen electrode, or the SHE. That's the half cell electrode that has a potential of 0. And then everything else is measured relative to that. So just like all these other values that we have, they're all measured relative to some standard that's on a table. Okay, so where these come from, we'll get to this in just a second, but in your notes, this is that standard table that they're talking about. So these are all standard electrode potentials. They're all written as reductions, so we'll get to that in a minute. But when we're talking about these values, this is what this is. So this is one table. They're in the back of your book as well. They're in a couple different places. Those are places where you can get those. Okay, so what we would use those for then is to calculate what's called the E cell, or we talked about before how it was called the electro-motive force. So what this tells us is this is the overall voltage that that particular voltaic cell could generate. So to get that, you're going to take, and these calculations are using, when we use this formula, we're using the values straight off this table. So even though these are all written as reductions, we know they're not all happening as reductions. That'll make a little more sense in a second, but we're using them off this table, and then we're going to put them into this formula. There's another way to do this, but I don't want to get into that right now, just because I think if we just focus on one way, that'll kind of keep it a little more clear. So you always take the E cell, or the E of the cathode, minus the E of the anode. So the first thing you have to do when you look at one of these cells is identify what's the cathode, what's the anode. We'll talk about how to do that in a second. Then when you plug them into this formula, you always take the E value for the cathode minus the E value for the anode. That gives you the overall E cell. This also allows us to determine whether or not that's a spontaneous reaction. So if it is spontaneous, you'll have a positive E cell value. So when you calculate this, E cell will be positive. If that value is negative, that means it's a non-spontaneous reaction. And that particular reaction, as you've got it set up, won't generate electricity. And we'll do some examples again in a second. So here's that table I was talking about. So these are all written as reductions. So even though when we look at the voltaic cell itself, it's not, one side is going to be an oxidation, one side is going to be a reduction. When we do the calculation, all you do is take them off of here. So don't worry about the fact that these are all written as reductions, even though that's not what's happening for some of these when you put them into that equation. We're just going to take these values off this table as they are. Okay, so here's an example of that. So it says use the standard electrode potentials, which again, that's what that table is that you just had, to calculate the standard cell potential. So when they ask for the standard cell potential, that just means you're calculating E cell. And these standard potentials, those come off of that chart that's on the previous page. So this is the electrochemical cell at 25 degrees. Okay, so when they give us this overall reaction, if they don't tell us, like if we're not setting the cell up, then we have to figure out what's the oxidation half reaction, what is the reduction half reaction. Because if you remember on that previous page, to calculate E cell, you have to know you're going to take E for the cathode minus, so cathode minus E for the anode. So if you remember from Friday, the only way to be able to tell what the cathode is and the anode is to figure out which is reduced, which is oxidized. So remember we talked about anox, red cat. So before we can do any of these calculations, we have to look at this and figure out what's going on. So this is going to be my easiest one. So I'm going to start with the aluminum and the Al+3. So I'm going to get rid of this for just a second here so that I can take this down. So I have aluminum going to Al+3. So I'm going from a 0 to, I'm sorry, I made that a plus. This should be +3. Aluminum to a +3. So this one is losing electrons. So this is my oxidation rate, half reaction, which means this is my anode. Okay, so this would be anode. That means the rest of this is my reduction half reaction. So that's my cathode. Okay, so NO3 minus plus 4H plus goes to NO plus 2H2O. Okay, so that's where I go to my chart here. Okay, so I'm going to go down and I'm going to look for aluminum. So notice it doesn't look exactly like what it looks like on here. So on here, it goes from Al to Al+3, but if you look on the chart, it's Al+3 to aluminum. That's what we mean by all of these are written as reductions. So we know that in this reaction, aluminum is being oxidized, but we're going to use it because of the formula that we're using. We're just going to pull that number off of here. So if you find where that aluminum is, that value is negative 1.66 volts. Okay, so that's the number we need for the anode reaction. For the cathode reaction, that one's going to be up here a little bit further. So that one is positive 0.96 volts. Okay, so that's what we need to start. So then we're going to go back to our formula. So E cell equals cathode minus anode. So I'm going to plug those values in. So this is my cathode value. So 0.96 minus a negative 1.66, and that gives me 2.62 volts. So that's my standard cell potential for that particular reaction. Okay, the other thing we notice here is this is positive, which means this would happen spontaneously. So the way that's written, the way that's set up would be, that would give you a spontaneous reaction. That would generate electricity on its own if you had those two reactions happening in separate cells. Okay, so that's one form of how you could potentially have to use that E cell equation. And just like always, stop me if you have any questions or you're not sure where I got numbers. Make sure you ask questions as we're going along here. Okay, so when we predict the spontaneous direction, we can also use the chart to do that. So the half reactions with the more positive electrode potential attracts electrons more strongly and undergoes reduction. So the half reaction that has a more positive electrode potential is going to be your cathode. So that's going to be what's at the top. So when you're looking at that chart on that previous page, when you're identifying what the cathode is, what the anode is, you're going to compare the positions of the two things that are in your setup. Okay, so say you're using like aluminum and iron or aluminum and zinc. You're going to look at their relative positions on the chart. Whichever one is closer to the top of the chart, that's going to be your cathode. So substances at the top, those are good oxidizing agents, which means they're going to cause other things to be oxidized. So the ones that are the top, that's going to be your cathode. The one that's closer to the bottom, that's going to be your anode. So when you're given just the setup and it says, here's the two metals you have, set up the cell, this is how you determine what's the anode, what's the cathode. So if you want something to be spontaneous, the one at the top, closer to the top, is going to be your cathode. The one at the bottom has to be your anode. Okay. So then the one that has the more negative electrode potential, that's going to repel electrons and that's going to undergo oxidation. So that's the one that's your anode. That's the one that's going to be by the bottom. So those are good reducing agents, which means it causes the other substance to be reduced. So any reaction in that reduction potential is spontaneous when it's paired with the reverse of any reaction listed below it. So that's what we mean by, these are all listed as reductions, but when you're going to reverse one of them when you're doing the actual problem. When you take the numbers off of this chart, you leave them as they are. So like we said, you're never going to change the sign of anything. You're going to leave them like you are when you put them into that formula, but you'll see what we mean by the reverse is going to give you that spontaneous reaction. Okay, this one sounds really confusing, and I think we're actually going to, no, let's go ahead and do the first one. We're gonna modify how we're doing this just a little bit. So it says, predict which of these reactions is spontaneous, and then if it is spontaneous, we're going to draw the cell for it. If it's not spontaneous, this is the part we're not gonna do. We're not gonna flip it around because I think that's going to be too confusing in this, the way we're having to do this. So you'll see what I mean here, and then that's why we're going to do that other practice together, because that's a good, solid, straightforward practice so we know what we're doing here. Okay, so this is what we mean. So this is our first example. So in order to do this, we want to first figure out, is this potentially a spontaneous reaction? So to do that, I have to split it up into its half cell. So as written, this is what it would be set up as. Now, if we were going to go ahead and label this little chart here, these would be the solid metals would be your electrodes, and then the ions would be what's in solution. Okay, so that's what that little setup would look like if we're going to do it like this. So we have to first label things as what's oxidized, what's reduced. So if Fe goes from 0 to +2, then that's losing electrons, so that's oxidized. Okay, so that means that would have to be the anode. This one then would have to be reduced. So that would be the cathode. Okay, so this is where we're going to figure out whether or not this would be spontaneous as written. So we're going to go to the chart and we're going to look those values up. So if I go and I find the iron, irons is -0.45. And if I look up magnesium, that one is -2.37. Okay, and then I'm going to put those into my E cell equation. So E cell equals E cathode minus E anode. So cathode, -2.37 minus anode minus 0.45. Okay, so this is going to be -0.237 plus 0.45. So you can see from this, this is going to give me a negative voltage. Okay, so that's going to be a negative E cell, which means this one is not spontaneous. Okay, so I'm not going to do anything further with this one. I'm going to identify this as not spontaneous. The way it's set up is not going to work. So we're just going to leave it as is. Okay, we're not, now what the question originally was asking you to do was to then flip those and make it spontaneous. We're not going to do that because, like I said, I don't think that translates well the way we're doing this particular example problem. So we're going to leave it as is. So now we're going to go to the next one, and we're going to see one that is spontaneous, and then we're going to finish it up in terms of identifying what's going on in that particular set. Okay, so for this one, we're going to start the same way. So we're going to say we have Fe going to Fe plus 2, Pb plus 2, going to Pb. Okay, I'm going to go ahead and label my metals here. And then identify my anode and my cathode. So this one, losing electrons. So this is my oxidation. This one, gaining electrons. This is my reduction. So that means this is my anode. This is my cathode. Okay, now another way you can do this is if you look on that chart, you can tell whether or not something is going to be spontaneous based on how their relative position. So if you have iron being, and I know this is hard to see on what you're doing here, trying to look at my paper through the camera here, but if you find iron, iron is down here at the bottom, and I can't see the camera right now. So iron is down here at the bottom, and then lead is a little bit further at the top. So since lead is above iron on the table, and like we talked about, the cathode has to be above the anode, that means that this reaction will be spontaneous. Okay, so then we can go ahead and look at our overall values for this. So our value for this one, so the E for this one is negative 0.45, and these values come from the table. So I'm taking those straight off the table. The E for this one is 0.13. So if I want the overall E cell, then I'm going to take cathode minus anode. So 0.13 minus negative 0.45. That gives me an E cell of 0.32 volts. So positive E cell means spontaneous reaction. Okay, so because this one is spontaneous, then I'm going to go ahead and fill in the rest of my diagram here. So once you have that set up, if you remember, there are a bunch of things we talked about for these voltaic cells if you have the reaction set up as a spontaneous reaction. Okay, so then what I can do on here is I can label a couple things based on what we just figured out. Okay, so we talked about the iron was your anode, so I'm going to label this, and this is what you're going to have to do on most of these, is you'll have to set up the cell, calculate the E cell, and then label the diagram. That's what it'll look like on the homework quiz. So that's your anode, this is your cathode. It'll ask you to label the charges of the electrodes. So the anode is always negative, the cathode's always positive. So if you remember, a negative ion, anion was, and then cation was positive. That tracks the same with this. Anode is the negative one, cation's the positive, or the cathode is the positive one. The electrons move from anode to cathode. So it's going to ask you to show the electron movement. So the electron goes this way. And then in the salt bridge, it'll a lot of times say label the salt bridge. So that's my salt bridge. This little piece of whatever that is there that is soaked in some kind of salt solution that allows those electrons to move through. And then it'll sometimes ask you to show the direction of the electron flow in the salt bridge. So if you remember, we talked about how the electrons have to go all the way around to complete that circuit. So the negative ions are going to go this way. So they're going to go to the left, or they're going to flow towards the anode, which means to balance the charge out, the positive ions are going to go in the opposite direction, and they're going to go towards the cathode. Because the main idea of the salt bridge is it has to balance the charge. So you can't have a buildup of one charge on either side in order for that cell to flow. Okay, so that's the idea behind this one. That was everything that this particular question asked you to do. The next thing I want to do before we stop today is go through one more example. So before we move on to that next, and like I said, we're going to do this next. Any questions on what we've talked about so far? Everybody doing okay so far? Okay, so what I've done here is I've took that picture and pasted it into the slideshow here. So what we're gonna do, get rid of this too, is we're gonna start, like this is the best way I think to move through one of these problems. So what they give you is they're gonna tell you what the two electrodes are, or what the two metals are that you're going to make this out of. Okay, so if you look on your paper, it's probably a little easier to see on your paper than what's on the screen here. They're telling you you have aluminum and you have lead. That's all the information you're given here. So you have aluminum and lead. It tells you what they are sitting in, and it tells you the molarity. But from there, you're going to have to set this whole thing up. And what I would do is I would kind of go through this process before you even really look at the questions, because almost all of these are going to ask you to do the same thing. So the first thing you have to do is you have to figure out, what is my anode, what is my cathode? Because my goal here is to set up a cell that is spontaneous. So you're going to identify what should be the cathode, what should be the anode, to make this a positive E cell. When you do that, you're going to go to your chart. So if you look on your chart, you are going to look for aluminum and lead, okay? And these are the same two that we did a minute ago. So aluminum is, or no, they're not the same two. I don't think we used aluminum before. Aluminum is on the bottom, lead is on the top, okay? So that means in order to make this a positive E cell, the one that's on the top has to be the cathode. So aluminum's further down. So aluminum, I'm going to make my anode, and then lead is going to be the cathode. Okay, and again, the reason I'm doing that is because cathode is higher on the table than aluminum is. So if it doesn't give you the overall equation, if it doesn't tell you which is which, then you're going to assign them so the E cell is positive. So whichever one is higher on your chart, that's going to be your cathode. The one closer to the bottom is going to be your anode. Okay, so that's your first step. The other thing to remember is if they give you this setup, the one on the left is not always going to be the anode. Sometimes they're flipped. So you can't assume just because aluminum's on the left, it's the anode. There's no like set standard anode has to be on one side, cathode has to be on the other. So always go to the chart, always check that first. Don't just assume because one's on one side, the other is on the other side that you can label them that way, okay? It makes more sense when they're set up like this, but it's not always going to be the case. Okay, so that's step one. So then, now that we have this labeled, then I know that the electrons are going to go in this direction. So the electrons are going to flow from anode to cathode. So that's something else that it's going to ask me to do. So I'm going to show the direction of the electron flow. When they come back around to the salt bridge here is already labeled, but I can go ahead and also show the direction of the ions in the salt bridge. So I know the negative ions are going to flow. They're going to track with the electrons so that it goes all the way around to complete that circuit. That means my positive ones have to go in the opposite direction. Okay, so I'll label my salt bridge that way. In solution over here, I have aluminum nitrate. So really the only thing I care about is this Al+3. Like we said, this nitrate's just floating around in there. It's not going to cause any issues, it's not going to react with anything. It's just a spectator ion. Over here, I have Pb+2. And you can see that if you look on your paper, you can see that a little better. On the paper, you can see that it's AlNO3,3, PbNO3,2. That's where I got that +3 and +2. So I'm just uncrossing charges from that formula that was given. Okay, other thing I can do before I move forward here is I can, I know the anode's that's where oxidation's happening, the cathode is where reduction's happening. And while I'm looking at these, and actually I could have done this when I was looking these up, is I'm going to write down the E for each one of these. So E for aluminum was -1.66, E for lead was -0.13, okay? So that's the overall setup. Now I'm going to go through and we'll work through these questions, and you'll kind of see why I did this first, because this pretty much answers all these questions. We just kind of did all of this to start with. One last thing I am going to do here, though, just because this will help us in a second, is I'm going to write the reaction that's happening at each side. So on this side, aluminum is going from aluminum metal to aluminum +3, and that's because it's losing electrons. So these electrons are leaving that side because it's changing from aluminum to aluminum +3. So as those electrons leave, then the aluminum piece of metal is kind of going away here, and it's becoming aluminum in solution. On the other side, as those electrons go into this solution, this lead ion that's in solution is picking them up. So for every 2 that go into the solution over here, this becomes lead metal. So those start getting deposited onto this electrode over here. So this electrode is going to kind of disintegrate, whereas this electrode is going to get bigger. And that's because the aluminum is losing electrons and becoming aluminum ions. And then on the other side, those electrons are going into that solution, and that lead +2 is picking them up, and it's becoming solid lead, which then plates on that lead electrode. Okay, so that's kind of the overall what's going on there. Okay, so then let's look at the questions. All right, so on this one, first question is which is more easily oxidized? So basically what that's asking is what is the anode? So they're saying which one of those 2 is the anode. So we identified that on the previous page as aluminum. So aluminum, this side over here, that was my anode. Balance equation, that's why we wrote those 2 equations out. So we did Al goes to Al +3, and then Pb +2 goes to Pb. Okay, so when you have to do the balanced equation, you're going to have to add those electrons in on your own. So for this one, if it goes from Al to Al +3, then it gives off 3 electrons. The lead, like we said a second ago, picks up 2 electrons, become lead. So now if you remember from balancing redox reactions, to get the overall balanced equation, we have to balance those electrons out. So this is kind of a very simplified balancing equation. So this one, I would have to multiply by 2. This, I would have to multiply by 3. Okay, so I would have 2Al goes to 2Al +3 plus 6 electrons. And then I would have 3Pb +2 plus 6 electrons goes to 3Pb. Electrons would cancel. So then my overall equation, which I'm going to write up here, would be 2Al plus 3Pb plus 2 goes to 2Al plus 3 plus 3Pb. Okay, so that's where we would get a balanced equation for something simple like this. And these would always be that simple. If you had to do a balanced equation, they'd be very simple like this here. You wouldn't have to deal with like H's and waters and all that kind of stuff. Okay, next one, maximum voltage. That's where we use our E cell equation. So E cell equals cathode minus anode. So that's why we wrote those on there earlier. So if you remember, this was a negative 0.13 for this side. And again, this was my cathode side. And then this was a negative 1.66. So then I can just plug those into that equation. So cathode minus anode minus negative 1.66. So the overall voltage is 1.53, and that should be positive because that's how we set it up. Direction of electron flow, we labeled that earlier. So it goes from aluminum to lead, or if you had it, you could just draw it on there. So you could just show that the electrons are going in this direction like we did on the previous diagram. Positive ion flow, we said was going from, the positive ion flow was going from Al. Let me get rid of some of this over here so I can write this back out here. from Al to Pb. So the positive ions are going in the same direction as the electrons, if you want to remember it that way, or if you just track those electrons around, I feel like that's the easiest way to do it. The electrode that's decreasing in size. So that means which of those electrodes is getting smaller because it's losing electrons. So the one that's decreasing in size is always going to be the one that's losing electrons, okay? Because the ones the electrons are going away from. So that's going to be aluminum. The one that's increasing in size is going to be the one that's gaining electrons. So as those electrons go in, those ions are becoming solid metal. So that's going to be the lead. And again, we kind of talked about that on the previous one. Okay, next couple questions. Concentration of Al ions. So that means these ions that are in solution, is the concentration of those ions going to increase or decrease? So if you think about what's happening here, the Al is losing its electrons, so it's going from Al to Al plus 3. So those aluminum ions would be increasing, because as those electrons are leaving, it's putting more Al plus 3 ions into solution. The Pb ions, on the other hand, on the other side, these ions are going from Pb plus 2, and they're becoming metal. So like I said, they're becoming deposited on that other one. So those ions that are in solution would be decreasing in concentration. And again, that's always gonna be the same. So whichever side is the anode, those ions are going to increase in concentration. Whichever side is the cathode, those are going to decrease in concentration. Voltage at equilibrium, this is something we haven't really talked about yet, but if equilibrium is happening, if you think about like G values at equilibrium, if something's at equilibrium, the voltage would equal 0, or let's label that as E cell. So you can think of this is kind of like a dead battery. Once a battery dies, it's reached equilibrium, that value is 0. The anode we already identified, so anode was aluminum, cathode was lead, positive electrode, that's always going to be your cathode, and then negative electrode, that's always going to be your anode. So in that case, it's aluminum. Okay, so that's why I said that sometimes it's easier just to diagram the cell first, then you can go through and answer the questions. The practice that you'll do, it asks you to do all these things, but it doesn't make you answer all the questions. So basically all you would have to do is what we did on that first page where we just did all the diagramming on the cell. So I think this one, we're gonna have to do some taking pictures of your work when you do your homework quiz, because there's not really a good way. I don't know how to code well enough to be able to put something like that in there where you're drag and dropping like you do in the homework. So you'll just have to do it on the paper and then take a picture of it, or just draw it out. If you don't want to print the quiz out, you can draw it out so that I can tell where everything is. So you do that first, and then if there's questions, if you have that cell diagrammed, then that makes it easy to answer those questions.